everyone to our BDTI Skills Studio. It's very great to have you all here. Today we will be talking about classification and predictive analytics, and we'll be discussing a use case based in Slovenia around climate data. So without further ado, let's get into the agenda of the day. So for those of you who have been here before, you know the drill. For those of you who haven't, this is the running order of the day. We'll have a quick introduction to BDTI. We will get into the workshop then. We'll have a Q&A at the end, and then we'll wrap up and discuss some next steps and some next events. Please do remember to share your thoughts in the chat, ask questions in the Q&A or in the chat. Let's have a nice discussion at the end of this session if possible. Do feel free to share your learnings with your network, and do keep an eye out for future events and register for them. So what is BDTI? So BDTI is an enabler for a data-driven public sector. It's a free, ready-to-use analytics platform based on open source tools and cloud infrastructure. It's a place where public administrations can play with data, test their ideas, implement pilot projects for a duration of 6 months. It can support public administrations that maybe don't have access to their own infrastructure or resources, providing them with ready-to-use tools to experiment and prototype with data-driven products for public good. Next slide, please. So the infrastructure offers tools at every stage of a typical data journey, from data collection to processing to analysis to visualization to decision-making and everything in between. Next slide, please. I guess the big question is, are you eligible? So if you work for or represent a local, regional or national public administration in Europe, you're eligible. If you are in a university or in the private sector and you have a clear collaboration on a use case with a public administration in Europe, you're eligible. If you're not sure if you're eligible, or if you have a worthy use case, you can reach out to us and we can develop something together. We can work on a use case to solve real challenges that affects and changes people's lives. So the next slide, please. And we'll see who's using BDTI now. We currently have multiple public administrations working on really interesting pilot projects across sectors like urban insights, mobility, environment, and more. So you can read all about these on the website. We have some nice listings and stories for you to get an idea of what you can do with BDTI. So applying is straightforward enough once you have an idea of what kind of challenge you'd like to solve for. If you've got a use case in mind, if you're not sure, again, please reach out and we can build something together. And of course, you can learn more about the process on our website, or do get in touch if you'd like to have a one-to-one session about how we can build something. So without further ado, I will hand the floor over and we'll kick into today's workshop. So yes, thank you for joining us once again and enjoy the session.
Thank you, Kim. Hello, everyone. My name is Jordi Ricard, and I want to welcome you all to our workshop, Harnessing Climate Data, Classification and Predictive Analysis for Tourism. We are thrilled to have you all here, and we are excited to dive into the session today. Predictive analytics are crucial into today's world. The availability to use historical data to predict future events can transform how we make decisions, both in the business and in the public administration. When you can anticipate trends, identify risks, or discover opportunities that might have been hidden before, you gain a powerful advantage. And that's what we are going to explore today: how predictive analytics works and why it's so relevant. For public administrations, the potential of predictive analytics is immense. Think about all the challenges that governments face: managing resources, improving public services, addressing environmental issues, or even responding to emergencies. Predictive analytics allow agencies to move from reactive decision-making to proactive planning. For example, in the context of tourism, like we'll be discussing today, governments can use climate and visitor data to predict the best times to promote tourism, allocate resources, or plan for high and low seasons. But it goes beyond tourism. The insights gained from data can help administrations allocate resources more efficiently and serve the citizens better. As we move into today's practical use case, I encourage each of you to think about how predictive analytics could be applied in your own work context. Predictive analytics isn't just about crunching numbers. It's a powerful tool that can drive better decision-making, improve services, and ultimately make a significant impact on the communities we serve. So reflect on your experience. Think about the challenges you face in your current role or organization. Where could predictive analysis help you? Right? Consider, could you be predicting service demand? Could predicting the service demand help you allocate resources better? How might it improve public safety or emergency preparedness? Can it inform urban planning or other departments? Identify opportunities for improvement. As we go through today's workshop, think about how similar techniques could be applied to the issues you encounter. Ask yourself, what data do you already have access to that could be leveraged to produce predictive analysis, as we'll see today? And think beyond today's workshop. Predictive analysis is flexible. It can be applied to many different use cases beyond what we are covering today. How could predictive analysis help you anticipate future trends or changes in your field? And as Kim mentioned, after the demo, we will have a Q&A session, and we encourage you to share your thoughts or ask your questions. If something sparks your interest, bring it up. This will help us all think more creatively about how predictive analytics can benefit our work. With that, let's move into the use case. Now that we've seen the importance of data analysis and forecasting, let's go to our use case today. We'll be trying to answer a specific question. That's the basis of a good use case. Have a very specific question to answer. How can the public administration effectively use TCI, the Total Climate Index, based predictions to engage tourists and promote outdoor activities through digital platforms? That's the question that we are focusing today. Throughout the session, we'll be using open data sets from the ECAD portal, which offers a wealth of information of aspects on the weather, and use that to do that prediction. So before we deep dive, let me explain what the TCI stands for. This is Tourism Climate Index. The TCI is a measure used to evaluate how suitable weather conditions are for outdoor tourism activities. It combines factors like temperature, humidity, wind speed, and sunshine to give an overall score that indicates whether the climate is ideal for tourists. For example, a high TCI score means that the weather is great for activities like hiking, sightseeing, or visiting outdoor attractions, while a lower score might suggest that the weather is less favorable. In our case today, we will be using TCI-based predictions to help local governments recommend the best outdoor activities depending on weather conditions. Weather prediction is widely available in the short term, but long-term predictions struggle with accuracy, so calculating the TCI can become difficult. We will use machine learning training on historical data to predict the TCI when only partial data is available. Forecasts for things like the mean temperature on specific months are more reliable than for precipitations, so we can use those to predict TCI. Open data refers to freely available data sets that anyone can use, modify, and share. This concept is especially relevant for public administration, as open data fosters transparency, collaboration, and innovation. Governments around the world are increasingly releasing their data to the public, enabling researchers, business, and citizens to develop solutions to urban challenges. In this workshop, we'll be using European climate assessment weather datasets. These datasets are publicly available, and you will see how we can analyze and visualize this information to derive valuable insights. The importance of open data cannot be overstated. It provides a foundation for transparency and community-driven innovation. Not only does it offer an opportunity for cities to improve their services, but it also allows the private sector and civic tech communities to build on this data to create smart data-driven solutions. Additionally, there are millions of open data sets available through platforms like data.europe.eu. This European-wide portal hosts data from various sectors and regions, covering topics from environmental sustainability to transportation, public health, and more. These datasets are free for reuse and can empower public administrations to improve urban planning, resource allocation, and policy development. In today's workshop, as I said, we'll be using the ECAD daily climate data from Slovenia. Right? That's the country we've chosen. This dataset features daily observations collected from various meteorological stations across Europe, providing a comprehensive view of different climate factors such as wind speed, humidity, temperature, and more. In this case, we'll be using stations in Slovenia. Each data point has undergone quality controls, ensuring reliability, with flags indicating the status of the data, marked as OK, suspect, or missing. By leveraging this dataset, we can explore how to analyze historical climate trends and apply predictive analysis to inform decision-making in sectors like tourism, public health, and environmental planning. First, predictive analytics doesn't happen in isolation. It relies heavily on having good and clean data. We'll be working with a combination of climate metrics using open data sets. The goal is to show you how this data can be processed and transformed into something actionable. We are going to walk through several important steps in this process, from cleaning and preparing the data to building machine learning models that make accurate predictions. To make all of this happen, we'll be using a combination of tools available through the BDTI platform. Specifically, we'll be working with Jupyter Notebooks for the data science aspects and Min.io to store and manage the data securely. The steps we'll follow today. We'll start with the data collection. We will gather the climate and tourism data from the open data sets, and we will ensure that these data sources are reliable and relevant. The second step will be the data cleaning and preparation, where we will remove duplicates, correct any errors in the data set, handle missing or incomplete data, and put our quality control measures. We will also normalize and format the data suitable for the analysis, and we will create the features relevant for the predictive modeling. Then we will do the model building. We will choose the appropriate machine learning algorithm, and we'll split our existing data into training and testing sets for the model evaluation. Once we have that, we will train our models, in fact, using the historical data, and we will assess the model performance with the metrics like accuracy and precision. Once we have that, we will deploy and go to our decision-making, which will be implementing a small application that uses this prediction on new data that we will be entering to inform and guide decision-making process. To ensure we have enough time to cover everything thoroughly, we've pre-recorded this demo with my colleague Berta. This allows us to focus on each step of the process without rushing. But don't worry, we'll still be around while you're watching. Feel free to ask any questions that you come up with the chat. My team and I will be actively responding to your queries and as far as the demo plays. We'll make sure to address any questions at the end on the Q&A after the demo, and we can deep dive deeper into any part of the process or tools that you are curious about. So without that, let me move to the recording. Watch closely and don't hesitate to put any question in the chat.
Let's get started by setting up the tools that we'll need for this workshop. So starting off from the BDTI website, I'm going to go into the portal and access it with our credentials. And then once we're inside, we will see this initial dashboard. We'll navigate to Service Catalog and look for the tools that we need. So as we mentioned before, we need two tools for this workshop. The first one is going to be Jupyter Notebooks Jupyter Lab for data science. It's this one here. So I'm going to click Launch to start the configuration process. First, we'll give it a name. This is usually the name of the service and dash the initials of the person who is creating this service. This is so we can later identify who on the group we're going to share this deployment with has created the instance. So it will be Jupyter Lab -cp. We'll make this shared for the ClearPix group. And then we'll select one of the predefined configurations. In this case, we're going to need a medium one. This will automatically set the CPU and memory resources for us. And if we were working on a smaller or larger project and needed more compute resources, we could set a small or a larger or even custom configuration. This automatically sets a password for us. We will be able to retrieve it later from my data. So we just have to select the NFS, which is the shared storage with all the people in the group. And then if we get rid of this service deployment and we just terminate it, we will still be able to retrieve later the things stored in this NFS. So let's launch it. Good. So now we're going to continue. We're also going to need min.io for object storage. So just launch it to configure, and it will be min.io-cp. We'll make it shared for the same group. And in this case, just a small configuration. This again sets an admin and username and password for us. We can set the username. So we're going to use user1, the password, and that's it. So click launch. Now this might take a few minutes, so we have to wait until these deployments are created, and then we will be able to retrieve them from my services and the access credentials from my data. Now we have the deployments ready. We see here the Jupyter Lab and then min.io. We're going to start with setting up min.io. I'm going to open it and sign in. The username and password, again, we can get from my data. So let's look for the min.io service here. Min.io admin username, which is administrator, and we will copy the password. We'll log in. And now the first thing we need to do is to create an access key. So navigate to access keys here in the left menu and create a new access key. This will give us automatically a username, so an access key and a secret. We'll hit click create. And now, just like the message says here, this is the only time we will have access to this. So make sure to copy it temporarily, maybe in a notebook or somewhere safe. Because again, we will not have access to it. So let's close this. And now we see a new access key has been created. So we have this stored, and we will also need the URL. So it's this part here, min.io dash and the number. So also store this in a text file or somewhere safe. And now let's launch the Jupyter Lab deployment. So let's look for Jupyter Lab. Copy the password. And open it. And we will see the main page, so the launcher. And on the left menu, we can see the NFS. So these are the shared files that we shared with the other people in the group we selected in the configuration process, and also with other deployments that use the same NFS. So if we, again, terminate this instance or this Jupyter Lab deployment, we will still have access to the files that are in here. We can start by creating a new folder for the project that we're working with. You can click here on new folder or right click and add a new folder here. We already have a folder set for this project, so we're going to double click it to access it. And we see all the files stored inside of it. But first we need to set up and just prepare the environment for the workshop and the use case. So we're going to be working with this European climate assessment dataset, and we have created a custom query, and then this downloads a zip file that we already have ready. So what we can do here is just drag from our file explorer the zip file with the data. So if I drag and drop here, We have imported the zip file with the data that we downloaded. Next, what we're going to do is to import any libraries that we might need during the use case. So right-click and create a new file. And we're going to create a file named requirements.txt. This is the best practice if we want to import more than one library at once, because it makes it easier. We only have to import one line and then just keep adding all the list of libraries we need in this requirements.txt. So we're going to save this and close. Now to actually import these libraries in the txt file, we'll go to File, New, Terminal. So here we are in the main directory and we need to move inside the Climate Quest folder. So cd Climate Quest. Now we're inside that folder and we need to run pip install r and the file with the requirements. And if we click enter, this will install any libraries that we might be missing. In this case, we already have all of them installed. So we can close this. And another thing we need to prepare is the credentials for the access to MinIO. So to do that, what we're going to do is right-click and again, new file. And we're going to name it .n. It already exists, so probably we're not seeing it because this is a hidden file. So let's go to View, Show Hidden Files. Yeah, exactly. So we have the .n file here. To access this hidden file, we need to go back to a new terminal here and enter nano.n. Nano is a terminal-based text editor. If we click enter, yeah, we can see the MinIO credentials. This is just commented out. And here we have the password, the access key, and also the URL that we saved. So MinIO dash the name of your group, .svc, and then 9000. You will have this file you can use it as a template on the GitLab repo. Just make sure to change the part of the URL that you need to change, then the access and the secret keys. And once you're done, click Control X, the Y just to save it and enter. And we can close this. Now we're going to create a Jupyter notebook just to start working with the data and writing some code. Just to create a new Python 3 notebook, you can either select it directly from the main page if we're in the launcher, or right-click, New Notebook, and select the Python kernel, or from File, New Notebook. Let's write some Markdown. So Markdown is a simple language that allows you to include formatting instructions directly in the text. So bold, italics, hyperlinks, headers, and more. And to do that, you have to click on the cell outside of the code area and turn it into Markdown from here, or we can click M. And now this has become a Markdown cell. So if we click here and add some text, so this will be a header, normal text, we can add cursive. And when we run this chunk of code, so click here on the play button, we see that it is on the format that we set. To write code, just make sure that the cell is in code mode, and you can run anything. For instance, print hello world, and run this. We see the output directly underneath each cell. So this is great for experimenting, as we can run the code bit by bit and see that it's doing what we expect, or do different tasks in different cells. Now, we're not actually going to use this new notebook. We have one ready that you will have in the GitLab repository. So let's delete this one. And we will start by cleaning the data. So let's open the clean data Python notebook. Now I'm going to do a step-by-step breakdown of what this notebook is doing. It's essentially cleaning the data, but let's see what each chunk is doing. First, we're importing the necessary libraries. So those that were missing, we can add them to the requirements.txt file and then run pip install as we saw before to install them. And then we call them from the notebook here. Next, we're getting the credentials from the .env file that we have created. And then this chunk essentially creates the Minio buckets for the raw and clean data. We will call them raw data TCI and clean data TCI. And the code first checks if buckets with such names already exist in our Minio deployment. And then it creates them if they don't exist. If we run this, we will get that the two buckets already exist. So let's check it from the Minio console. If we go to Object Browser, we will see that indeed they both already exist. So let's go back to the code. The zip file that we dropped here contains a zip file of the country, and then for each measure, a zip file inside. So this next chunk extracts the zip file inside the zip file and stores it in a folder with the same name. Next, we're uploading this data that we have extracted to Minio with the same folder names. So let's take a look at how this looks from Minio. In raw data, we have one folder per measure, and then one file per station of that measure. So each station for each measure will have a separate file. Let's take a look at this one here, for example. We can download it and we can see here the file. So this is the format that it has. There's a column indicating the station ID, the date in which the measure was taken, the actual measure, and then a column with the quality of the measure. So it will be 0 if it's okay, 1 if it's expected to be wrong, and 9 if it's missing. So now if we go back to Jupyter Lab and to the next chunk of code, which is this one here, we will now read the contents of the raw data files one by one, and then aggregate them into one big data frame. So the aggregation will be done by weather station and date. So now we will have one row per date in each measure station. As you see here, December 1st, December 2nd for the same station. And we have had to add a column with the station ID. Then combined all the measures in one unique row. Now all the data will be transformed and used to calculate the tourist climate index, or TCI. And the data frame has for each measure a quality column, as we saw, for that measure. So we will set values in the column to none, so to missing, since the measure is or might be wrong and could affect our analysis. And then we will drop the quality measures to keep only the measured values. So we will have only the measures here. And if it was either 1 or 9, we just set it as missing so that it doesn't affect our analysis. Then we reformat the date and we reformat it to date time to be usable. So now after that, it looks like this. Finally, we convert the values to match the units we want and drop all rows with null values. So this is what it's done here. We're dropping the nulls in this other chunk of code here. So now with these values adjusted, we can convert them into the standardized units that are used to calculate the TCI, the Tourism Climate Index. And you can get more information on this on the reference document that we have in the presentation, which you will have in the GitLab repo. But this long chunk of code here just standardizes those to be able to calculate it. And then once we're done, we're just creating this clean data into the clean data TCI bucket and uploading it. And then we delete any temporary files that we have created on the way. Just to point out that this is now, we have one unique data set that is in the format that is actually useful to analyze later. And this will weigh less than the raw files. So it will be good for analysis and for compute. Next, we can go to MinIO console, then in object browser, see the clean data TCI, and see that this is way less. So the TCA data weighs way less than the total raw data. The goal of this project is ultimately to predict the TCI values when part of the weather data is missing. And since there are 6 values that are used to calculate the TCI, there are a lot of possible combinations of values that can be missing. 63 to be exact. So we will have to create something that generates these 63 prediction models automatically. And we will now create a new script in Jupyter Lab, which we will call train models IPython notebook, where we will set up everything. So I'll walk you step by step through this script. It's train model. The first thing we do, as always, is to load the necessary packages. And then what we're doing is loading the process data from MinIO into memory. So we create the same client as before and download the CSV into a pandas data frame. The TCI score is usually categorized into 3 groups. TCI under 40 would be bad. TCI between 40 and 60 will be okay, good. And then TCI greater than 60 will be very good weather for just doing tourism activities outdoors. So we will create this small function that classifies the category number given the TCI score and applies it to each row in the data frame with a new column. So it's this last new column on the right called TCI category. And it will be what's known as the label, so the value that the classification model will try to predict later. The rest of the columns, so HU for humidity, sunshine, etc., are the features of the dataset. So they are the values that are used in training to predict the label. To start off, we do a test classifier where we only omit the sunshine hours variable. And we create 2 new data frames, one with the target column TCI category and one with the features used for training. So all variables except for sunshine. And we split them into train and test ratio on 70-30 ratio. This is what it's done here. And the model is now trained and we tested with the test dataset. So the result shows 0.9 accuracy out of 1, which is nice. Now moving on to the big model. So the following Python class handles the training, storage, and usage of the classification models. And the idea is that you can give it a list of named features to make a prediction, and it checks if a model with that specific combination of feature exists. And if it exists, it gives a prediction, and if not, it informs the user that it needs to be trained. This requires all models to be trained one by one, which we need to do automatically because it's 63 models or combinations. And for this, let's first create a list of all possible combinations of features, which is this list here. Now we iterate this list and train the models using each combination of features. So this process of training all possible combinations, so 63 models, can take a few minutes. In our case, it took 7 minutes. And the process also requires a bit more memory than usual. So this is the reason why we created a medium-sized deployment when we were preparing the tools. And if you get any Jupyter kernel error during this phase, it's likely due that of a lack of memory. So we have it already trained. And we can save it to the disk, so we don't have to retrain it in the future. We are saving the model, and then we're saving it also, storing it in the MinIO bucket just to have access to it later. So now we can test it out. We can just delete a few features and just see the accuracy of the model with those combinations. But seeing a score like this is nice, but it's not realistic to do this with all 63 models just to check the accuracy of each combination. So we needed to think of something different. And in this case, what we will do is for each specific amount of features, so 1 through 6, we will determine the best and worst combination of features possible to see which ones are most important for determining the TCI category. Here's the code that does that from 1 to 6 features. And then we plot all of these into a graph where the blue line represents the best combination possible for each number of features, and the red represents the worst possible combinations. So we can clearly see that precipitation plays a big role in determining the TCI, as it shows up in almost all the highest performing classifiers. And we also see that maximum temperature can be very useful when other data is missing, but mean temperature and sunshine are preferable to TX, so maximum temperature, if they are available. But the least important feature for the TCI is clearly the wind speed, which makes sense, which is FG. Wind has little impact on whether a day is sunny or rainy or if the humidity is high, so using it as a sole predictor for knowing if a day will be good or not is not a good idea. With the classification models trained and stored in MinIO, we can now move on to using them to make predictions. So now we will work with the third notebook. It's the one called Interactive Widgets IPython Notebook. I'm going to open it. And we will use notebook widgets to make an interactive UI to interact with the model. So it will take that prediction and give recommendations on what activities a tourist can do that day. And first we need to load the model from the MinIO bucket into memory. So we will do this the same way as before with the clean data. Afterwards, we define a list of activities alongside the minimum weather conditions required. For example, going to a museum or trying out a certain restaurant can be done under any weather, but going on a hike requires no rain, taking pictures of historical buildings requires good lighting, etc. So depending on the prediction that is made, different activities need to be recommended. So it will be a list as a tuple for each activity, and the first field has the description of the activity and the second one has the minimum weather requirement. Just as a reminder, 0 is bad weather, 1 is okay weather, and 2 is very good weather. Next, we define all the widgets to type in the weather information and define a function to make the predictions. So here's the function that does the prediction and prints out the result. The function first takes the values that were written and converts them into a float and sends it to the classification model to make predictions. Once the prediction is made, the list of suggested activities we created earlier is filtered, and the only activities included are those where the predicted weather is better or equal than the one required. So of the final list of activities, 5 are picked at random and printed out. The function is then called using the widgets, and every time the input is changed, the entire function is called again to have real-time interactions. Let's see all of this in practice. So first I'm going to the first chunk and running it. Then we're going to get the model from MinIO. Good. Now we're creating the list of suggestions, creating the different widgets and the function. And here's the result. So let's say we had a day with a maximum temperature of 25 degrees. We know nothing else, so just based on that, it's pretty good weather. So these are the suggested activities. Now, if we change this, we can say that maybe the maximum temperature was 10 degrees. See, this already changes, so it's dynamic. Then the mean temperature was 5 degrees. And it rained a lot, so 100. This is bad weather. So now we get suggested activities that are indoors or just do not require very good weather. Note that the idea is not for the end user to manually type in the weather forecast when they are visiting. So that would be way too tedious and not very useful in practice. But it's more for a website to automatically fill this out for any given date using the best available data at the moment and give recommendations to the visitors for the period they're visiting in. This can obviously be tailored to more specific activities to the region, that is being visited. So we can recommend specific restaurants, hikes that are of interest of the town hall, for instance, to promote those. So that's it for this practical part. Now let's go back to the presentation.
Good. So after that demo that you find it interesting, as I said, please keep sending your questions through the chat. Let me recap a little bit, as I was saying before, the different steps we did. And so we saw how we collect the data, how to download the data, and how to put it on our repository, all the data cleaning and preparation we've done, fixing the errors, normalizing the data, that was an important step, and then create the feature that in this case was the TCI itself, how we build a model, and well, in fact, all the models based on the data available for the prediction, and then the training and evaluation on creating the two models, the different models. As Bert explained, the idea is to, we did a little demo on typing in the values to do the predictions. Ideally, that would be integrated into your website or having another system feeding the data using those models to predict the activities. So let's go back. At the start of our session, we posed the central question: how can the public administrations effectively use TCI-based predictions to engage tourists and promote outdoor activities through digital platforms? And from our discussion, we found some key insights. By predicting the weather a day will be good or bad for outdoor activities in different regions, public administrations can tailor recommendations that drive local tourism to improve the quality of life for residents. For example, if we know that today is sunny and pleasant, we can suggest activities like hiking, skiing, or visiting cultural sites based on the current weather conditions. To take action on these insights, here are some recommended steps. We could be targeting promotion for local attractions, use the TCI predictions to recommend specific outdoor activities based on weather, boosting local tourism and supporting local businesses. We could enhance visitor experience, setting up a real-time information system to keep both residents and tourists updated on daily outdoor conditions, suggesting corresponding activities to encourage participation in local events. We could embed TCI widgets in tourism websites, integrate the TCI-based forecasts into the official tourism and city websites, so visitors can access real-time information about the best outdoor activities for the current weather. Or promote local events. Use the weather forecasts to highlight upcoming local events that align with favorable conditions. For instance, if a sunny weekend is predicted, promote outdoor festivals, markets, or community sports events to attract both tourists and residents people. As we conclude today's workshop, it's important to highlight how the tools and techniques we've explored, such as the predictive analytics and TCI-based models, can be applied to a variety of public sector challenges. By using historical data to forecast conditions and promote outdoor activities, public administrations can directly enhance local tourism, improve quality of life, and make more informed, proactive decisions. The key takeaway is that data-driven insights, like those from TCI predictions, empower governments to better engage tourists, optimize the use of local resources, and tailor services to meet both current and future demands. Whether it's predicting tourism patterns, improving public health services, or enhancing urban planning, the same principles can be used to drive smarter, more efficient decision-making. You are now equipped with both the technical skills using tools like the Jupyter Notebooks and Min.io, and the knowledge on how predictive analytics can create more responsive and dynamic public services. By integrating these approaches into your everyday work, you can better serve citizens and adapt to changing conditions. With that, it's time for you to try on your own. If you have a similar use case, you can find the slides, all the code, and the learning material in our GitHub repository. Before we wrap up, we will open the floor for any questions you may have. Please feel free to type your questions into the chat, and the team and I will be here to answer them. Thank you.
Yes, thank you so much, Jordi, for that session. And please pass on our regards to Berta as well for the super inspirational and helpful demo. Now it's time for some questions and answers. If anything popped up for you, if you want anything clarified, do feel free to pop your questions in the chat or in the Q&A widget. We have a couple of questions in privately. Please don't feel the need to post them privately. If you do have questions, you can just pop them directly in the chat. But here's a couple to get us going. How do we handle missing or poor quality data? A good question, I guess, from any of our workshops. Maybe I don't know if we've actually touched on that, so maybe we could touch on that now.
I will answer those questions.
Yes, I just maybe I'll give you a quick introduction. Alex is also here today to answer some questions, just in case you're seeing a new face pop up. So yes, thanks, Alex. Please take it away.
So your question was, how do we handle the missing data, poor quality data?
Or poor quality, sure.
Yeah, okay. So missing or poor quality data is really a common issue when working with weather data sets or say sensor data in general. Okay, so in our project, we address this by checking the quality flags, as Berta showed you, that were provided in the data set. No? So if the data is flagged or suspect as missing, we either exclude it from analysis or use the remaining valid data to make those predictions. No? So for example, in this project, no, if humidity or precipitation data is missing, the model, we've seen that it still can predict the DCI based on other available factors, like the temperature of the wind speed.
Great, thank you. Okay, we have another question in. How accurate are the predictions made by the models in this project? That's a good question, I suppose.
That's a nice question, and it's kind of related to the previous question. As you've seen, the accuracy of the prediction varies depending on, for our project, okay, and which features like the temperature, wind speed, or precipitations are available, right? So in the demo, the only variable that we have omitted is sunshine hours, okay, from the dataset, because just with that sunshine hours variable, we could achieve an accuracy around 90%. So if more critical weather data like precipitation is missing, yeah, the accuracy tends to decrease. No, so the more variables we have, the better will be the predictions made by the model. And as we start missing variables, we will start losing predictive value and predictive the accuracy, basically.
Great, thank you. I guess there's another question here that's sort of related. Guy asks, specific to the use case on weather, how accurate can forecasts be taking into account climate change?
Well, that's a very nice question. What we know, okay, that's basic in all our AA projects that are based on past data, is that over time it tends to correlate. No, so the more data we have about the past, the better our predictions will be in the future. But what happens when something starts changing really fast? No, if we're talking about changes in weather, of course, what we can see is that it has started to correlate with past data less and less. So yeah, it affects the predictions, reducing accuracy, of course, because it's not generalizing what we have seen in the past with what we have right now in the present, and what we want to predict in the future. So yeah, it affects.
Great. Okay. I think we have one more in. So please, if we still have time for more questions, if you have more questions, please do post them. How does MinIO handle large data sets, and can it scale for even bigger projects? So tool related question there.
Okay, so with MinIO, no, this technology is designed to handle large scale data storage. Okay, so we can easily scale to meet the needs of bigger projects, no, or smaller projects if we need to downscale. Min.io uses what we call object storage, no, which means that you can store massive amounts of structured and unstructured data, like these weather records that we have seen, or images, JSON files, or whatever file you have that it's unstructured that can be huge. No? So the storage is distributed across multiple nodes. Okay, so as your data set grows, Min.io can be expanded by adding more storage nodes, no? Without affecting its performance. That is what we're looking for, no? To grow and to scale properly. So on the BDTI platform, you can configure, I think you've seen that, or maybe in other webinars, the instance size. No? So what I mean with instance size is the CPU and memory based on the project needs, no? or even set custom resources.
Great, thank you. Okay, here's a question in from Dimitrios. He's asking about the type of tourism. So this model about tourism is helpful about a specific type of tourism, right? Because if we're talking about winter or sea tourism, then we would require different types of data sets or different types of algorithms. He goes on just to clarify. So basically the question would be, is it possible to generalize your model to handle all types of tourisms, or would we basically need different types of models? Could this be handled with additional tools?
Here, it depends of our approach. No? So if we want the model to generalize to different types of tourism, either we need a lot of data from all the types of tourism, so our model can learn from past data from all the types of tourism that we want to predict data on. Okay, so how could we handle the different types of tourisms? So we can always add some variables to our data set that is pointing which type of tourism do we have. So the model knows that it's basically different types of tourism. Or if not, we can handle different type of, or we can train different types of model on separate data sets, because you either have winter tourism or summer or sea tourism. No? You don't have both normally at the same time. So it makes sense to have separate models so that they will predict better on the data based on the data that you have. So we'll be much more specific. So it's a balance always into how much specific you want to be or how much you want to generalize. No?
Yeah, that makes sense. Always a balance. Great. Okay, I think that's all the questions we have. Yep, I don't see any more questions. So thank you very much for those questions and for your answers, Alex. They were all very, very helpful. If we didn't get to your specific question, do feel free to post it. Send us an email to our pilot's email address, which you'll see at the end of the presentation now, and we'll get to your question. So to wrap up then, if you wouldn't mind going to the next slide for me, Jordi. Yep, a lot of these workshops have passed, but we still have more. There is another one coming up in 2 weeks' time, more predictive modeling. We're talking about real-time forecasting and monitoring of bicycle use. And we have a couple more just added actually that haven't been added to this nice graphic, which if you sign up for our newsletter and stay tuned, you will be informed of. So there's about 4 more events to close out the rest of the year. So make sure that you register for those and catch up. And if you did manage to miss any of the previous sessions, don't worry, we've recorded them and we've put all the slides and code up on the repository, so you can catch up on what you missed, no problem. We'll go to the next slide, please. So yes, just to wrap up then, are you eligible? As we sort of mentioned at the start of this session, if you're a local, regional or national public administration, you are. If you want to collaborate with a public administration, if you're in academia or the private sector, there's also a chance you'll be eligible on a use case there too. And if you're not sure, do reach out to us here at this email and we'll figure it out together. So Yep, here's some nice QR codes for you to learn more about BDTI and to sign up to our newsletter to make sure that you don't miss out on notifications about future events and some news and activities that the BDTI team get up to. And that's it, I believe, unless there's another slide, that's it. So thank you so much for joining us today, and thank you, Jordi and Alex, and please send our regards to Berta for her perfect and really, really great demo. And we hope to see you again in future sessions. Have a good day, everyone.